Let's start with an introduction into OpenMP. So, what is OpenMP? It's a standard programming model for shared memory parallel programming. It's portable across all shared memory architectures, and it allows incremental parallelization, and that's important. So it's compiler based. The compiler has extensions for existing programming languages, and that is mainly by directives, as we will see, but there are also a few library functions. It supports both Fortran and C++ bindings, and OpenMP is a standard. So why would you use it? Well, in this graph you see time and effort, but time and effort is development effort. So how much time do you spend on creating your program? And on the y-axis is the performance. So what kind of performance do you get from your program? For a Scala program you have to invest some time and effort, but your performance is kind of limited, because of course you can only use a single core on your CPU in order to run your program. The thing you can do is to make your code distributed, so that it can actually run on multiple CPUs, but also even on multiple compute nodes. The problem is that in general that requires quite a rewrite of your code. And basically that means that during quite a lot of time and effort spent, your code just doesn't work, it just does not compile. And only then you start reaping the benefits and you get a very good performance. So in OpenMP the situation is a little bit different, because you can incrementally parallelize your application. So as soon as you start working on parallelization, you already reap some of the benefits. And of course, you do have to spend some effort in order to get to a certain performance level. And as you can see from the graph, actually the performance you can expect from OpenMP at the end of the day will be lower than that of MPI. But you can even combine OpenMP and MPI and gain a little more performance on top of what you would have without OpenMP, so just with MPI. So essentially, even if at the end of the day you would require MPI to parallelize your application, still the work you invested in OpenMP might be reused. OpenMP is the easiest approach to multi-threaded programming. It is actually easier than what you would do with pthreads, the fork-join model and so on, where you have to take quite a lot of care in order that things are correct and that your code doesn't crash. So OpenMP makes that a lot easier. Multi-threading is required to exploit modern hardware platforms. So Intel CPUs, AMD CPUs, they all support building blocks they all support threading, and hence you can use multiple cores from within your application. And of course there are other multi-core CPUs such as IBM Power CPU, but also for instance the ARM CPUs, which are getting popular. So where should you use OpenMP? Well, basically you would do that for the mid-range of programs, in the sense that the number of CPUs is not that large as for MPI, but it's somewhere in the middle. So depending on your hardware, you can run a shared memory application on, for instance, a compute node with 2 CPUs, which would basically give you up to something like 40 cores, or whatever, 64 cores if you have some recent AMD hardware. Of course, there are machines which have many more CPUs in a shared memory mode, and if you can exploit those, you can obviously scale up much more. Here are some examples of the scaling behavior of OpenMP applications, but of course your mileage may vary, because basically writing efficient OpenMP applications is not that trivial. But given good programming and let's say a problem that lends itself to an OpenMP approach, actually can get a very good performance. And of course, you get typically the best performance with hybrid execution if you're using many CPUs. So most OpenMP constructs are compiler directives or pragmas, and the focus is to parallelize loops with independent operations. So basically the iterations of your loop must be independent from one another. OpenMP offers an incremental approach to parallelism, so you can start by parallelizing, let's say, your most compute-intensive part of your application, and that will already give you some benefits. And then you can continue to do some lesser hotspots in your application until your entire application is parallel, if that makes sense. So on the on the left, you see a serial program that declares an array of 1000 elements. It runs over the indices of that array and does some huge computation on each of the elements. And note that those computations are independent, because in the call to do huge computation, only a single element of our res array is used at a time. So independent iterations, that's good for OpenMP. And the only thing which we need to do in order to parallelize this, so to ensure that the cores do some iterations, but not all, so that the work is actually divided among the cores, among the threads of your application, is add a compiler directive. So basically pragma OMP parallel for says that the for loop below it should be executed in parallel by multiple threads. So OpenMP is basically defined by the OpenMP Architecture Review Board, and a number of permanent members, and you recognize household names such as AMD, Cray, HP, which is now HPE, IBM, Intel, NEC, and so on, but also compiler vendors such as the Portland Group, which should now be NVIDIA, and some companies that no longer exist independently, like SGI, and in fact also Cray, because they became part of HPE. And there are some auxiliary members from academia and from national laboratories. So you might recognize EPCC, which is basically one of the English high-performance computing organizations. This is the timeline. So OpenMP started as a standard for Fortran in 1997 and for C and C++ in 1998. And those two standards developed independently up to OpenMP 2.0, and they were unified in OpenMP 2.5. And then there was a steady progress of new releases of the OpenMP specification up to the latest one, which is OpenMP 5, which dates to November 2018. So here's a bit of an overview of the capabilities and the features added into the specifications listed here. So we'll go over most of those features and also the more recent ones in OpenMP 4 and OpenMP 4.5. For more information, you can always consult the OpenMP homepage and the OpenMP user groups. And there's a listing of books which might be interesting. One I personally like a lot is the one by Georg Hager and Gerard Verlein, Introduction to High Performance Computing for Scientists and Engineers. It doesn't only talk about OpenMP, but also about parallelization in general and the influence of CPU architecture and compute node architecture on performance and how to address this in your programs.